Anybody start the homework yet? All right. See how that works. Not too bad. I'll have to remember to turn it around. So all we did last time, to make sure everybody understands where we are currently, we got up through section 1.3. I'm going to go really pretty quickly through 1.4 and 1.5, and then we're going to get into chapter 2, which is where we really start analyzing some data. And that's why you need a calculator today. And one of the basic things the calculator does for us is to sort data, which of course is really exciting. But the worst part about statistics is always data entry. So that's why you always see those summer jobs that are data entry jobs. They just want somebody sitting there putting stuff into a computer. I also want to show you one of my favorite websites. So I get that ready. All right. So let's first, real quick, all we did last time was talk about, well, we really talked about a lot, but we got through some definitions, we got through some basic ideas of statistics. I got a feel for what you guys kind of already know. There's a lot that people already kind of know. We're going to get a lot more detail today, and finishing out chapter 1, on different ways to collect samples. So we saw a bad way to do it. You guys are here. Let me use you guys. That's the convenience sample. Right? That kind of sucks. Another example of a bad sample is if you send out a questionnaire, which unfortunately is the way that very often happens in, for example, college. If they send out a questionnaire and they ask people to send it back in, what do you think would be bad about that? If I sent out 15,000 questionnaires and I got 8,000 back, over half back, that's still not a good sample. Could anybody figure out why that would not really be a good sample?
People that send them in are probably have a different personality or different answers.
Exactly.
People would not fill it out and send it back.
I like it. So there could be something that unites those people. It's sort of the same problem we had with you guys, me picking you guys. You're all here at this time. You're all in statistics class. You might have certain things that you have similar that might predispose you to go one way or the other that would throw my data off. People who voluntarily respond, which is what this is called, is a voluntary response sample, are normally, they feel pretty strongly. Very often it might be in one direction or the other specifically so that it doesn't average each other back out, right? One side might be like, well, it's not. The other's like, hell no. And they're calling in, they're paying 50 cents to call in or whatever. They're going on their favorite website and answering a freaking poll that doesn't mean a damn thing because it only polls people that go to that freaking website, right? So nowadays we see that all the time. You have news channels that you know the type of person who watches those news channels. So when they say, call us and tell you what you think, that doesn't mean a damn thing, right? So it's a little scary. I'll do that later. We'll get into the rest of this. So last time, just a real quick summary, we talked about qualitative, quantitative data. We talked about population, sample. If I said I take a sample of 87 Grossmont adjunct teachers, and I find that 11% of them like to watch infomercials. Right? What's my population? So I take a sample of 87 Grossmont adjunct professors. I find that 11% of them like to watch infomercials. What's my population? All right, be a little more specific. Grossmont adjunct professors. I like it. Cool. So if you just say adjunct professors, you mean all colleges. If you say Grossmont professors, I didn't include full-timers. Right? So adjunct is the same thing as part-time. What's the 11%? What would you call it? What's the term that goes with that? Be careful. It must be the statistic. Because the 11% came from what? My sample. Beautiful. So you've got to be really careful when you see them report a percentage or an average. Where did it come from? That came from my sample. That's just a statistic. You with me? Now 87 is actually a pretty large sample, especially considering that there aren't that many more than that adjunct professors. Got with me? There are more than 87 adjunct professors, but not that many more. So it's a decent sample, so I actually will feel pretty good about saying, well, it seems then that 11% of all adjunct professors, or close to it, like to watch infomercials. This is my infamously great creative mind this morning coming up with a great example. So what would that be then? If I said 11% of all Grossmont adjunct professors like to watch infomercials, that would be a parameter. Cool. All right. So that's some of what we talked about. And then we talked about nominal, ordinal, interval, ratio. I had a really good question after class the other day. I want to make sure everybody kind of heard it. You always give the answer as far as the highest level. So if your answer was age is interval data because I can subtract two ages and it makes sense. That's not right. You can subtract them and it makes sense, but you can do more. You can divide them and it makes sense. So your answer should be ratio. So I always get a few students who are upset. They're like, what do you mean? I can subtract? No. Well, you do more. So the answer is higher level than that. Cool. Okay. All right. So today we're going to focus on ways of collecting samples, and then we're going to focus on silly uses of statistics. You know, not just silly, but outright false uses of statistics. Cool. So the different ways to collect data, they're kind of doing the same order they got. Oh yeah, that's this. So we already talked a little bit about random sampling. Just remind me, what was the main idea of having, or trying to have, a truly random sample? Yeah, everybody in the population has an equal chance of getting in, so you should end up with a decently diverse, representative sample, right? So everyone in the population has an equal chance of being selected. Your end goal is to have a sample that's truly representative of the population. Now, just a really quick aside, if I used you guys as my sample, it is a bad sample because the method I used to pick it was bad. You could end up, it could be true that you guys are actually exactly representative of the population. I doubt it, but listen, it could be true, right? But I cannot accept the results because you picked it poorly, or I did. I picked the sample poorly. Now, I could go out and do a completely, amazingly random sample. I haven't left anybody out. Everybody's got a chance to get in. And I end up with a bunch of like 80 people that are all 5 foot tall, 28 years old, and drive a Hyundai. Right? I mean, that's completely possible according to probability. But I still, if I follow it, if I always make this my goal, I can then use the results. Now, if it's that obvious that the sample kind of ended up being, whoa, then you step back and you do it again. And you go, who the hell picked this? Is this really random? This is kind of crazy. But are you guys kind of with me? You always, this is your goal. It's just really hard for this to actually happen, but that's the best way to get here, is to do this. Let everybody have an equal chance to get. I'm not going to get into simple random. Later we'll get in the book they say something about simple random, which always freaks people out. And I'm noticing right now that I can't get away from it. I've got to talk about it. So if I picked one person from each row, right? I put one person here, one person, one person, one person. Is that random? If I like gave you all a number and I picked it out of the hat and I went down to each row just like that, is that a random sample I've done? Yes, because everybody has a chance to be in that sample. You guys with me? It would not be a simple random sample, and I know you guys are just like, Oh, I love statistics so far. It's all this frickin' terminology. I love it. You got to bear with me. Chapter 1 again. I got to remind you every now and again. You got to suffer through chapter 1. It's not simple random because for a random sample, each individual has to have an equal chance to get in. For a simple random, every possible subgroup of people has to have an equal chance to get in. So if I pick one person from each row, I can see a subgroup of people who could never end up together in the sample. These people. Could they all be in the sample together? So that's why it's not officially simple random. That becomes more important in chapter 7 when we start looking at statistics between samples, different samples and stuff. So right now, if you don't quite get the idea, let it go for right now. All right, I just had to say something about it, come to find out that every subgroup has an equal chance. The mistake people make is the minute I break you up into groups, I'll take 5 men and 5 women. It's not simple random. But people get it confused. They go, oh, groups. Random is about groups, simple random, so it's simple. No. The minute I break it up into 5 men, 5 women, can the sample ever be nothing but women? So then there's a group, any group of women, that can't all be together in the sample. Cool. Oh, all right. What about systematic sampling? What does that sound like? Systematic. If somebody's systematic about something. What do you think that might mean?
There's steps that lead up to it.
I like it. There's steps to it. There's some kind of process. There's some kind of, and what it ends up being is a very regimented process. Like if I'm on an assembly line and I pick every third radio to see if it's defective, that's systematic. If I'm a cop and I do every 5th car that goes by to see how fast people seem to be going, and obviously I'm not a cop. This is supposed to be my radar gun. No. If that's systematic sampling. If I do every 3rd song on the radio and see how long it is. If I take the temperature every 20 minutes, there's a system to every one of those things. So systematic is actually one of the easiest ones to identify. Right? Okay, so that's just every nth thing. That is an awesome definition. I love it. Okay, but I think you understand. Good. And then we already talked a little bit about convenience. Convenience is also pretty simple to tell. If somebody's standing outside of they happen to have to go to Target, and they stand up, they go buy some stuff, and they come out in front of Target, and they say, what do you think about stores like this? Really? That's convenience. You had to go there anyway. You're talking to people that are coming. That's convenience. It's not truly random. So normally convenience sampling will end up with a pathetic sample. So, not much to say there. Then we get to 2 that I want to set up a little bit here. Okay. And by the way, I never ask you just straight up definitions on a test. I'll never say, define stratify. I'll say, here's a situation, what thing is it? Right? And I might ask you to explain why. Sometimes there's 2 answers that might be okay, considering the way you're looking at it. Both of these, stratified and cluster, start with the same first step. The first step on both is break the population into groups. So this would be like, when I said each row, I'll take one person from each row. That's breaking my population into groups. If I said men and women, that's breaking my population into groups. If I said freshman, sophomore, junior, senior from a high school, that's breaking zip codes, so forth. Whatever little subgroups you want to break it up into, and then you take a few from each, that would be stratified. Stratified would be if there's like 3 classes in a row of statistics. So my population has been broken into 3 parts, and I take a few from each. And then those go into my sample. Do you remember the pictures? So if you took some from all, that would be stratified. You guys still semi with me? This one's the same first step, break it into groups. If I take all from some, that's clusters. So very often what you'll do is, for example, if I wanted to say something about the patients in California currently in the hospitals, I can randomly select certain hospitals and tell them, just give me all your patient records. That's easy. And it's valid. Why is, both of these actually are still random, they're just more specific ways to accomplish big random. Like I said, you guys agree with me. If I break you guys up into rows and I take one person from each row, that was still random sampling, because there's nobody in here who did not have a chance to be in there. You with me? Sort of? I like the look I'm getting from you. Come on. So both of these would end up with random samples. They're just more specific ways to do it. So if I talk to all the hospitals, and I well, actually I only pick a few hospitals and say, give me all your patient data, that would be clustered. That'd be a lot easier than going to every single hospital in California and say, give me a few patient records. No, it's much easier. Just send me all your records. Right? People go by. Okay, let me give you a little story. Back in the day, we actually had enough money to have January classes. Anybody remember that? They were like 3 freaking weeks. So I taught this course in 3 weeks. So the first day I said, you're all insane. Here we are. And one year I had a dude that had just come back from Iraq. And he said that, we started talking about this, and he says, dude, don't teach me about cluster, because cluster, I know, you can't even, I don't like it anymore. Cluster's bad. And there's a specific situation, so I got him to tell me the situation after class. And he said that there was a time when the U.S. wanted to see how Iraq was doing not too long after Baghdad fell. So they sent people there to investigate, and they were going to do some kind of sampling from all the neighborhoods and see how people were doing. Agree with me so far? The problem was, they broke all the neighborhoods up in these little clusters, right? And then you're supposed to randomly pick from there so that everybody has a chance. What they did was they said, I know it's safe here and here and here and here and here. Let's go there. Because I don't want to, I don't want to put myself in harm's way. So that is true. You can look this up. I don't know how easy it's going to be to find it on Google nowadays, but that's exactly what happened. So he didn't understand that it wasn't cluster sampling's fault. They just used it incorrectly. So it ended up not being truly random. Anybody who lived in those neighborhoods that they didn't go to, specifically didn't go to, didn't have a chance to be in the sample in the first place. They were excluded from the beginning. And in fact, it completely skewed the results, because the whole thing was about how are they doing in Iraq. Well, we talked to all the people where we felt safe going, and things going pretty good. What? All right, so there's always a misuse of things that make people distrust statistics. And it's not statistics' fault. It was a misuse of it. Cool. Okay. By the way, this is section 1.5. I decided to do that real quick. We're going to take one step back to 1.4, and I want to show you my silly example here. How's this guy doing? Good. So this is Discover Magazine. And there was a group of people. Well, let me actually just show you the article. This is Discover Magazine. And I don't know if you guys know Discover. It's supposed to be a reputable magazine about scientific breakthroughs and so forth. So here's this article. Let me just let you absorb what it says. Now, this is after they posted the original one. They came back in and kind of edited it a little bit. But look at you guys with me? So each cell phone tower creates 18 babies. So effectively what they're saying is, and this is true. This is not true. Let me be clear. That sentence is not true. This study is true. They did a study. They went out and they realized that the people that lived near a cell phone tower, or the area around a cell phone tower, had more babies than somewhere where there wasn't a cell phone tower. Okay, just let you absorb that. Now the problem that people have is when you hear something like that, what I just said is true. But our brain kind of naturally makes the connection for us, which is bad. It says, oh, cell phone towers must create babies or make women more fertile or men just more whatever. Right? Fertile, horny, whatever. You guys kind of with me? All right. Obviously, that can't be true. I hope you understand that. The cell phone tower radiation can't suddenly make that happen. Oh my, no. Right? When they first posted the article, it was completely straightforward. It said, this study's found this, it's amazing, oh my God. And it was actually kind of a prank. There was a group of people that posted this. It's actually a true study. But they just wanted to put it out there to see if somebody would jump on it and put it up as news. And they're trying to show how the news doesn't really check thoroughly and doesn't really understand things well enough to put up stuff that's really true. And this happened. They actually grabbed it and put it up and went with it as if it was true. As if their conclusion was true. Now, anybody have a better conclusion?
There's higher populations where there's more cell phone towers, so
I
there's
love
more
it.
people.
Straight up, right? If you have cell phone towers, it's probably because there's a lot of people there that need them. So if you have a lot of people, you're going to have more births, right? Okay. And there's some other things about if they would have done percentages, it's still, there's an argument, and this is a while back, so this is an argument about younger people have cell phones, so if there's a lot of younger people, there's going to be more cell phones, and younger people have babies more often, and so forth, so on. Nowadays, everybody has a freaking cell phone, so, right? Okay. Well, that's one little example of how this gets us in trouble. This idea of correlation versus causation. Correlation just says, here's another example, just to give you an idea. If I went out and watched some basketball games, let's say a researcher goes out and watches some basketball games, and he goes, man, everybody playing this game is tall. For the most part. There's a few short people. You know, Spud Webb back in the day. Everybody playing this game is tall. So I think playing basketball must make you taller. Very interesting. I'm going to start playing basketball. And I like to look, so you guys think. I mean, but that's a little too silly. This one is really hard to catch. If you saw that title, most of us would go, whoa, cell phone radiation, it doesn't kill us, but it makes us, it's the other way around. You guys with me? But if I say basketball makes you taller, all of us in here would go, well, that's shit. Right? Because we understand something about what makes people taller for real. So what's the true conclusion there, of course? Taller people would have an easier time with basketball, so that's why they go into it, for the most part. Even though I still play basketball, and I would not consider myself tall. Right. Okay, so that's causation and correlation. So they talk a little bit about that in the book. Causation is when you think that basketball causes height increase. You can never say a causation statement from observing a correlation. If two things are correlated, meaning if one goes up, the other goes up, or something like that, there's some kind of relationship between them, you can't say that one causes the other. There might be some third thing causing both of them, and it might have just been a coincidence. You can't say. You can just say, I see a correlation. Okay. Here's one of my favorite websites. And this is just one of them. Anybody know about Reddit, by the way? There's a subreddit on there called Data is Beautiful. And of course, there's statistics subreddit, but the Data is Beautiful subreddit, you should take a look at it sometimes. It's nifty. Don't know what Reddit is. Look it up. So anybody ever went to Gallup.com or heard about it? Okay, I understand. Those of us, anybody in here at all, like political junkies a little bit, like if there's a polls for a presidential election, are you watching them? Or about the same people that put, okay, I understand. But just to show an example of why I like this website. So they have these things where they've done studies and they have the headline about what it is they found. And these are not correlation studies, by the way. This is like party views diverge most on U.S. gun policy. And this actually, I looked this up this morning, and it's kind of interesting. These are the people that identify as Democrat. These are the people that identify as Republican. And this is the difference between the two percentages as far as are they satisfied with where we are on these issues. So are they satisfied on our laws on guns? Much fewer Democrats than Republicans say they are. And that's the highest difference between the two. It's more than, you know, the amount that you pay in federal taxes, which is normally considered the big dividing line between the two parties. Guns is obviously a huge part of each party too. That by itself is not enough just to go, oh, interesting. You need to know these things. Survey methods. Results for this poll are based on telephone interviews conducted blah, 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 with a sample of this, living in all the states. And they go through, for results based on this, and by the time we get to chapter 7, we're going to completely understand the sentence. Right now, we probably don't. One can say with 95% confidence that the margin of sampling error is plus or minus 4. So it's sort of like they say 29% of Democrats are okay with where we are in guns, give or take 4%. That's like I was saying the first day, we're going to actually see the formula that gives us this. Okay. So that's one reason I love this, is because it doesn't just give you the headline, it gives you the backstory of how the hell they got there. One of the few sites that does that. Okay. So, now I want to focus on chapter 2. So let me just say this about chapter 1. If you haven't started chapter 1 homework yet, you desperately need to. There's a few things that I didn't do in lecture. Like I said in my email before, chapter 1 is really kind of more on your shoulders to get in there and read, do the homework, go back with questions. Cool. Since we just finished chapter 1 homework, what does chapter 1 homework do? Semi-official, yeah, next Wednesday. Cool. You have until the day of the test before, kind of late though, so. Huh?
Basically, just don't get behind.
Exactly, don't get behind. It's really weird. For some reason I feel extra geeky today, so just, I don't know why. Probably because I'm teaching statistics. Let me tell you let me warn you a little bit about chapter 2. When you go to do chapter 2.2, section 2.2 and 2.3 homework, you want to do them at the same time. 2.3 references what you do in 2.2. So I always have somebody turn in 2.2 homework and then they email me, can you scan that and send it to me? Because you do all the work in 2.2 to kind of build the pictures that 2.3 wants you to make. So do them kind of together. You'll see what I mean when you get into it. So I purposely assigned the problems so that it references back to the same problems you did in 2.2. So try not to get off track there. Okay. The whole idea with chapter 2 in general is how to present data. Just some visualizations you can make with data. 2.2 is all about creating what's called frequency distributions, and 2.3 is all about histograms. I like the word distribution. It's hard to not sound drunk when you say it. Distribution. At least it is for me. How many of you guys have ever heard of a histogram? A few of you guys. How many of you guys have heard of a bar graph? Most of us, right? So a histogram is the numerical cousin of a bar graph. A bar graph would be like, I would go out and I see how many people are driving Fords, how many people are driving BMWs, how many people are driving whatever the hell. That would be a bar graph. So the data that I use for this, is it qualitative or quantitative? Yeah, qualitative. It's names of cars. All right, so bar graphs are for qualitative data. Histograms are for quantitative data. So your scale, you can have a real scale. Is this a real scale? Of course, Ford before BMW. No, there's no scale. I can change those around. Here I'm going to have a true scale. I like that, Jeff. 1, 2, 3, whatever. Okay, cool. So here's why we need the calculator to help us out with this section. We're going to have kind of possibly large collections of data. And I want to be able to sort it so I can see easier where things fall. Right? So let's do this. Let's see if you guys are willing to do this with me here. Let's see. So we got a lot of people. So let's see. I'm going to randomly pick a few people from each row. Is everybody in here willing to tell me their age? Anybody not willing? Okay, here we go. So if I kind of point you out, tell me your age. 23. Back there. Right, 22? Oh, 22? Yeah. 24. Okay. It'll still work even if I don't quite get the person I'm pointing at. 26. 22. Behind half. Yeah. 19. Way in the back.
21.
21. And then one of you guys. 19. 21. 19. Up here.
21.
21.
19.
19. Let's see. In the back.
22.
22. Up here.
30.
30. I like it. Closer to me there. You. 19. 21. Control. Yep. 22 in the back, and then glasses.
30.
30. Okay. 22. 30. I hope you're not offended by me calling you glasses.
No.
I'm going to get some names eventually. I know your names like glasses. 16? Okay. 20. In the way back. 19. Y'all, I wonder if anybody's like, is he going to do some kind of weird math magic with this stuff? But 20. Let's see, one more. Way back. 21. Okay. That's a decent little collection of data. So, it's not the best. Obviously, I might have some hidden bias or something that maybe picks certain people or whatever. But, getting past that, just so we can get some data, some real data that I can use. And in fact, what I normally do is, don't forget those surveys you have to fill out. I saw a few of you guys. Don't forget there's 2 of them. Because I have like 8 did one and 6 did the other one. There's something wrong there. What I do very often is I'll pull data directly from that to put into quizzes and tests. So that you're actually analyzing your own group. Real data. So let's do this. Let me show you how to input this stuff into the calculator. Okay. All right, and if you're borrowing the calculator, the unfortunate part about doing technology like this is you have to be very honest with me if you hit a problem. Don't hesitate to stop things if you hit a problem, because I want to make sure you're coming with me. And it's good for me to see all the different errors that you can create. I don't know if I've seen them all yet.
Did you have any more access?
No, sorry. I think that'll work all right. Let's see, actually, I think it should work all right. Okay, cool. Stay. So the very first thing, and if you look on your calculator Bible, at the very top, I try to put some very basic things, because how many of you guys have actually never used the TI before, or maybe just turned it on once before? Everybody in here has used it before? That kicks ass. All right. Or a few of you guys just don't want to say, that's all right. I try to put some very basic ideas on the top. So for example, stuff like, it's just like a scientific calculator. You can see everything at once, thank God. So I can do something like this, and I can see it all. I can move around to edit it. So a couple things you probably don't know. If I wanted to take the square root of that number, I really don't want to waste time and just write in all the stupid digits. There's a kick-ass little quick memory button that holds the last number that was on the screen in memory. And that's right down here, the little A and S. You see that right above the negative sign? So if I hit square root, this second button's like shift, second, negative sign, square root of the answer, that's going to do the square root of this thing. So it should be like 7 point something. Cool. All right. And then one other little thing, if I realize that, oh shit, that should have been a plus up there, if you hit second, enter, it pulls up the last thing you put in. Hit second, enter again, it goes back to the next thing that was there, and then you can go back and edit it. And of course, you want to probably edit in the right place. Okay. All right, so that's some basic stuff. But it sounds like most of you guys have used this before, which is good. Right now, which button do you think is probably going to be most important to us?
Stats.
Yes. So right here, the little stat button, right in the heart of the calculator, bam. And to put data in, you want to use edit. Notice right now you've got sort, two different kinds of sorts, ascending, descending, clear list. Number 5 is if your lists get freaky. So everybody do this for me. Go ahead and you can either hit the number 1, or you can just hit enter if it's highlighted. Now you might have stuff in it, but does everybody have L1, L2, L3? Is anybody missing one of them, maybe? You are?
L5.
Oh, really? All right. Because if I go up here and I hit delete, accidentally trying to clear it out, you have to hit clear to kind of clear a list out. But look, my L2 is gone, my L1 is gone. If I come back out and come back in again, it's still freaking gone. That sucks. Because a lot of what the calculator does is it defaults to L1, L2 to do a lot of stuff. So you don't want to just go, I will accept that my L1 and L2 are gone, and I'll move forward in life. No, screw that. I want them back. So that's what that setup editor thing is for. You hit 5, enter, you go back in, they're back. Thank God. So then I can go up, if you have data in them, go ahead and hit the up arrow until you're highlighted and hit clear, enter. Over, up, clear, enter. All right, so let me know now, everybody doing okay with that? Because we all have different levels of being comfortable with calculators. Okay. So now just put the data in. And of course, I'm in a great position to do this. Just like that, just put all the data in. Hopefully you can read my writing. So exciting. Okay. So now we want to sort this, probably from lowest to highest. So if you go back, hit stat, and then number 2. So you can either hit the number 2 or you can scroll down and hit enter for the second guy, sort. And notice how it looks sort of like a function. It's got a little parentheses waiting for you. You have to tell it which list to sort. So tell it list 1 and list 2, all those lists are up here. So hit second 1 for L1. So now I'm telling it to sort ascending L1. Enter. Okay, which is sort of anticlimactic. It says done. All right, but you got to go back in and see the results. Stat, edit, and then now everything's in order. Okay. So far, you're like, well, that's not quite worth the money I paid for this, but that's just one little thing. Yeah. So, what I want to do is, I want to get to the point where I can create a histogram, which will basically, I would assume for us it would look something like this. And my assumption is there's a lot more people who are younger, and even before we actually got the ages, we all kind of knew this. 2 reasons. 1, this is community college. Most of you probably came right out of high school or not too long ago. And 2, this is a day class. Where would this distribution be different? Night class, because there's more adults. More, not just adults, but more older adults in night class. Cool. So that's my end game. I want to get to here. I want to create this picture. But we got to talk about what does this really represent then? These widths of the rectangles, what does that really represent? How do I get that from this? So what's my lowest age?
16,
What's my highest age?
30.
30. Cool. I didn't include myself on there. That would have made that a little higher. Here's the idea. I want this to be roughly 16, and I want this to be roughly 30. I want to cover my entire range of ages. That's pretty straightforward. So the first thing we really have to figure out is how many rectangles do we want to use? And then we got to figure out how wide in years does each one have to be. So it's sort of the same idea to think of something very physical. If I wanted to panel this in wood for some really weird reason, and I got to figure out, well, okay, how wide is this? How big do how many wood panels do I want to use? And then they'll tell me how wide they all have to be. It's a very physical problem, really, to cover this thing. I don't want to be short at the end. That will look even worse than actually making it to the end, right? And I don't want to try to go over, because then they're not all going to be kind of the same width. You guys kind of with me? Okay, so it's kind of nice. It's a math problem, but it's very physical. It's got a very visual you could use. So I need to go, how far do I have to go? What kind of range of ages do I have here? 14. So the range is 30 minus 16, 14. And you can always use between 5 and 10 classes. The book says 5 to 12. For us, it's going to be 5 to 10. We're never going to have, thankfully, thousands of data points for us to put into the calculator. Screw that. So we can use between 5 and 10 classes. So how many classes? Let's use, it's a pretty small sample. So let's use 5 classes. You can imagine, if I had a small sample and I used a lot of classes, they might all be one big. It doesn't really show me anything, right? So I don't want to use that many classes here. So what I do is, if I have to go 14, and I want to use 5 classes, how do I figure out how wide each one has to be? So if I wanted to go 20 feet, and I only want to take 10 steps, how far does each step have to take me? 2 feet. What'd you do? You did the distance I want to go, divided by how many steps, in this case, I want to use. So here's the distance I want to go. Here's the steps I want to use, the classes. So you just divide. So what's 14 divided by 5? Yeah, cool. 2.8, which you round up, always round up, because they have to be at least 2.8. I really don't feel like using 2.8. That'll make all my work a little bit ugly. So this comes out to be 2.8, rounded up to 3. So if I make all my rectangles 3 years wide, that will definitely cover the data. It'll over-cover the data, but in this case, it's fine. I just want every data point to have a place to go. Is that cool? Okay, okay. Got a few people at least making me feel all right. Okay. So, the thing about statistics that we all know is, I'm sure you've heard the quote about lies, damn lies, and statistics. Maybe you've heard that, I don't know. It's an old Twain quote. All right, so now you have. But everybody distrusts statistics because, unfortunately, a lot of people misuse it. And one easy way to purposefully misuse statistics is to make a graph misleading. To use a weird scale. For example, if I wanted to show, look, I say, here's men's salaries, here's women's salaries. Oh my God, there's obviously a big difference, but maybe not that big. Maybe what I did was I started at 40,000, 50,000. So my scale is misleading. It didn't start at 0, so it overpronounces differences. You guys kind of with me? So the fact that we have some flexibility. How many classes do I want to use? We could have used 6. We could have used 7. What point do I want to start at? We have these flexibilities, which kind of makes it possible for people to misuse it. So in general, it only makes sense to kind of start at 16 in this case. You could start at 15, especially if it kind of ended up with like 15, 20, 25, 30. That's always nice. But most of the time, you want to start at the actual first data point. So if we start at 16, here's the weird thing. I want my width to be 3. So where should the next class start? 19. Good. So the next class would start at 19. But what's wrong if I do this?
You can't have data doubled.
Where would I put a 19-year-old? Would they go in the first or the second or both? Do I count them twice somehow? Are 19-year-olds somehow twice as worthy as anybody else? The 19-year-olds in here might think so. You guys with me? So obviously, really, what do I have to put here then? 18. Okay, cool. This is not really true, but it still is a width of 3, 16, 17, 18. Not really, but we'll get there. So this is the hardest part about this method. This is the book method. I'm going to show you a method that I was taught that I personally like better. But you certainly can still do the book method because you have the book to back you up. But I'm going to show you another way to do it that you can use too, whichever way you like better. The quickest way to do this then is to put the first number down, then start adding 3. Add 3, and then come back up here and go 1 below that. Then add 3. Add 3. You guys kind of with me? Cool. And then this will be 25 to 27. And then finally, you doing it? Yeah, you can do it, John. 28 to 30. All right. This is not excessively difficult ideas. There's a little bit of ambiguity in here. And let me address this issue right now. Remember what our end goal is to be here? Why do you think I don't want... what would be wrong if I made this picture and it ended up looking like this? You can see why somebody might think it has to look like that. What's wrong with that? What does somebody who's looking at it say to themselves if they see all these gaps?
There's gaps in the data.
Did I leave people out? Does that represent nobody's in there? Do you see? So you don't want any gaps in histograms. So this method is, and I personally really don't like this method, but a lot of books are using it for some reason. Don't take that to mean you can't use this method. Do. But it ends up with this thing you got to cover somehow. So really what's going on then is there's these numbers on the outside. So really this first class goes from 15.5 to 18.5. You guys see how I got that? And then this class would go from what?
18.6.
18.5
Oh,
to 21.5. So now you see how those match up? Will there be any gaps now when I make the picture? No, they'll both match up at 18.5. The next ones will match up at 21.5. There won't be any gaps then. So these are called, and yes, since we're out of chapter 1, that doesn't mean we're out of definitions. These are called the class limits. And these are called the class boundaries. So I always think about it that I have a limit. This is the limit of me. This is where I stop, right? But this is my boundary. Don't be getting in my boundary. So this is where the class stops, but this is the class boundary. Okay, maybe. Just to show you right now, the other way to do this. The first class, if I wanted to do it the other way, the first class would look like this. And then the second class. And you can see why people don't like this. It involves X, it involves inequalities. But do you see how there's no ambiguity? Where would 19 go?
in the second.
Because this is less than 19. This is equal to 19. So there's no ambiguity about where 19 goes. I don't need class boundaries. My class limits are my class boundaries. So if you understand this and you're comfortable with this, do this way. If you don't, you must use these limits on your picture. Okay, good. You're good. You're all excited about that. Okay. So now, all we have to do is add up how many things are in each of these. So how many 16 to 18-year-olds do I have? One. Sorry. So there's one. This is the frequency. How frequently does data show up in each class? So in 16 to 18, there is one data point that is in there. Yes, ma'am.
According to doing it that way, 30 is not included in your 5th class, so how would you do that?
Oh, it is. Over there, all you have to do is it's
just-
accepted to
You
me.
accept it, okay.
Yeah. What about 19 to 21? How many do I have there? $13? No, 12? I lost count. I think it's 11. So 19 to 21, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11.
I have 11.
Cool. Right. So this is just tallying up how many people actually show up in each class. This is going to actually relate to the size of my bar, because the highest bar should be where the most people are. So 22 to 24? 6? I like it. So 6 there. 25 to 27? 1. And then 28 to 30? 2. I like it. So I can sort of see the shape is going to be 1, 11, 6, 1, 2. So I can kind of see it. It's a little bit different than what I predicted, which is fine because it's a little subsample of this group. Okay. So what I'm going to do is I'm actually going to hold off. Well, actually, we can do this real quick. Because remember, I want to do that little field trip today, too. So in about 5 minutes, we'll be heading out on a field trip around the campus. So section 2.3, this is section 2.2. And one thing that makes it easier for humans to understand what the hell's going on here is to make this into percentages. If I make this into percentages and not just pure numbers, then it's easier for us to tell where most is and so forth, especially when there's a lot of stuff going on. So that's called relative frequency. So relative frequency, relative to the total number, how frequently does something show up in each class? So how do I make a percentage for the first class?
1 divided by 12.
In fact, what's going to be on the denominator?
21.
Because how many people do I have in my sample? Yeah, it's 12, 18, 21. Yep. So this will be 1 out of 21 which is just under 5%.
It's 4.76.
4.76. This will be 11 out of 21. Bless you.
52.38. Uh, 28.57.
And of course, a quick check. What should those all add up to be? Now, will it come out to be 100%?
Close enough.
Probably close, because we've rounded, right? It might be the rounding kind of takes us back to 100. So don't freak out if you get 100.7 or 99.5, as long as you don't get 92% or 112%. Okay. So this is section 2.2, which is putting together a frequency distribution. That's what that is. How does the frequency get distributed amongst all the classes? Okay, cool. Section 2.3 will then be how do you make a histogram based on that result. So I think we can do that real quick. You guys look like I'm getting drowsy. I understand. So since I'm officially doing the bookway, if you don't want to do the bookway, that's fine. But since I'm officially doing the bookway, I have to use these boundaries here. So it'll be 15.5 and then 18.5, and you just keep adding 3 because that's my width. Okay, cool. And that's the other good thing about the class boundaries. You can actually see the width in between them. The 3 is in between those two. And then here, let's say I want to make a relative frequency histogram. So what kind of scale should I use here? The worst thing in the world is to go, all right, 4.8, 9.7, 28.6, 52 point, yay. Your scale has to be consistent, right? It has to have the same amount between each. So if I need to get all the way up to freaking 52.3, I want to say maybe 10, 20, 30, 40, 50. Cool. And then just draw your rectangles in. So this isn't overly taxing to do. So this will be 4.8, so it's roughly just under halfway.
Do we always use the relative frequency as our y-axis?
No. So if I ask you for a relative frequency, you want percentages. If I ask you to make a frequency histogram, you just use
Okay.
the pure numbers, yeah. And then this guy will be 28.6, 4.8, so another one way down here, and 9.7, so just get up from there. Cool. Okay. So we had a couple outliers. We had the 16, and we had a couple of 30s, and it kind of gave me some unevenness to it, but it's basically what we would think it would be. Okay. So that's section 2.2 and 2.3. So next time I actually have a little worksheet that we're going to work on in class together. And I've got all the steps kind of spelled out so you can create your own histogram from some data. Right now what's going to happen, go ahead and